Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to my channel. In continuation of Power System Protection series, today our topic is induction motor protection. Induction motor is a truly workhorse of the modern age. So before we discuss the protection of induction motor, first of all we shall see the advantages of the induction motor. Induction motor are very cheap when compared to the synchronous and DC motor. This is due to the modest design of the induction motor. The starting torque of the induction motor is very high, which makes the motor useful for operation where the load is applied before the starting of the motor. The speed variation of the induction motor is almost nearly constant. Induction motors are maintenance free, unlike a DC motor and synchronous motor, as the construction of induction motor is very simple and hence maintenance is also easy, resulting in very low maintenance cost. Now we will see the protection of induction motor. The induction motor cannot be considered in isolation. On the one side, it is connected to the supply, possibly through some kind of power electronics controller, and on the other side it is mechanically coupled to the load. So we can say this is the block diagram of an induction motor. So the induction motor is subjected to large number of fault and operating conditions. These are described as, if we see the supply side, following abnormal operating conditions can be observed. For example, faults on the motor terminals, unbalanced supply voltage, single phasing, reduced supply voltage, and reversal of the phases. As far as the induction motor is concerned, there are phase faults, ground faults, and inter-turn faults can be observed in induction motors. So as far as the load side is concerned, we can say the failure of the bearing, overload conditions, and rotor jam. These are the abnormal operating conditions and the faults in an induction motor. So as far as the protection is concerned, first of all we shall discuss the starting current. An induction motor draws a very large starting current of the order of 6 to 8 times the full load current if started direct on line. The amplitude of the starting current may be comparable to the fault current. Therefore, the overcurrent protection provided to the motor must be able to discriminate between genuine fault and overcurrent due to the starting of the motor. So coordination between the starting characteristics of the motor and the overcurrent relay is required. From the figure, overcurrent relay characteristics must be above the starting characteristics but below the thermal characteristics of the motor. This will ensure that the protection relay does not operate during starting phase, will positively operate when the load exceeds the motor thermal capability. In electrical faults, first of all, faults on the motor terminals. The phase fault current at the terminal of the motor is large than any normal current, such as starting current or any inter-turn fault current. So a high set of the instantaneous overcurrent relay is recommended for the fast, reliable, inexpensive, and simple protection. The next step is the phase fault inside the motor. Protection against phase fault as well as the ground fault can be provided using either fuses or overcurrent relays, depending upon the voltage rating and the size of the motor. Most of the motors will be protected by HRC fuse or a circuit breaker. The fuse current should be greater than the starting current of the motor. The fuse operating time should be less than the permissible locked rotor time of the motor. Big motors, which are high voltage motors, will need to be provided with an overcurrent protection. The thermal capability characteristics of the motor should be kept in mind while applying the overcurrent protection. The overcurrent relay characteristics should be below the thermal capability characteristics. Now we will see the ground faults inside the motor. In case of a high impedance ground fault inside the motor, the fault current may happen to be less than the full load current. Such faults are difficult to detect using an overcurrent approach. Shows an arrangement for detecting high impedance ground fault. The three-phase line conductor carrying a current to the motor form a primary of a current transformer. The secondary consists of a pickup coil wound on the core. When the motor is running normally, the instantaneous sum of all three line current is zero. So there is no net flux in the core. Hence the pickup coil does not have any voltage induced in it. Now consider a ground fault. In case of a ground fault, the three line currents do not sum up to the zero, but they will be equal to the fault current. So in this case, there is a flux in the CT core. So the pickup coil has a voltage induced which can be sensed by the electronic circuitry. Now we will see the interturn faults. Interturn faults on the same phase are difficult to detect because they do not cause appreciable change in the current drawn by the motor. However, such faults cause hot spots to develop, leading to the deterioration of the insulation. No specific protection against the interturn faults is needed for the most motors except very big motors. For big motors, embedded temperature detectors may be relied upon to provide protection against interturn faults. Now we will see the abnormal operating condition from the supply side. An induction motor is subject to many abnormal operating conditions as far as the electric supply line is concerned. So first of all, unbalanced supply voltage. Large induction motors are very sensitive to the unbalance in supply voltage. The negative sequence component which comes into the picture because of the unbalance in the supply. This is because the motor offers a very small impedance to the negative sequence current. In fact, the negative sequence impedance is less than the positive sequence. So a 4% negative sequence supply voltage causes more than 24% negative sequence current to be drawn by the motor if the starting current of the motor is 6 times the full load current. This causes increased heating of the stator. Therefore, for large motors, any unbalance in supply voltage needs to be quickly detected and corrective action must be taken. Single phasing can occur because of the non-closure of one of the pole of three-phase contactor or a circuit breaker or a fuse failure or similar causes. Single phase cause negative sequence current to flow. The motor has a limited ability to carry the negative sequence current because of thermal limitation. Single phasing causes the motor to develop insufficient torque, leading to the stalling, making the motor to draw excessive current, and finally leads to burnout unless the motor is tripped. Next is the reduced in supply voltage. The torque developed by the induction motor is proportional to the square of the applied voltage. Therefore, any small reduction in the voltage has a marked effect on the developed torque. The reduction torque may cause the motor to lose the speed and draw more current. So large motor should be disconnected when a severe low voltage condition persists for more than a few seconds. Under voltage relays may be used for the protection against reduced supply voltages. Next is the reversal of the phases. When there is a reversal of the phase sequence possible due to the reversal of the phases, the motor rotates in the direction opposite to its normal direction of the rotation. In several applications, such as hoists and elevators. This is very serious hazard. So in such situation, a phase sequence detector, which is generally a part of under voltage or over voltage or a negative phase sequence protection scheme, can be used to trip the motor. Now we will see the abnormal operating condition from mechanical side. First of all, we will see the failure of the bearing in the rotor jam. In bearing failure of the rotor jam causes excessive load torque on the motor. This is reflected in the increase in stator current. Thermal overload relays offer a good protection against short, medium and long duration overloads, but may not provide protection against heavy overloads. Long-time induction overcurrent relays offer a good protection against heavy overloads. Combination of the thermal overload relays and the overcurrent relays provides complete thermal protection. And this is all from today's session. You can ask any question in comment box and your question will be answered accordingly. Thanks for watching. If you like this video, then please like, share and subscribe. Thank you.